Greetings and welcome to my new calculus channel. My name is John Gabriel, and today I'm going to be talking about nomenclature. Okay, and what does nomenclature mean? So let's have a look at the dictionary. I always am convinced that a good starting place to understand what is being said in any discipline or science, or in fact in any relevant field of study, is to look up the meaning of words. So nomenclature has a special meaning. It's a noun, and it means the devising or choosing of names for things, especially in a science, okay, but also in any other discipline. So it's very important to choose the right names for objects in any particular science. And there are a lot of problems with mainstream mathematics because of the use of, let's say, not very well thought out nomenclature, okay, nomenclature, however you pronounce that. So nomenclature has to be thought out very carefully in order to give objects, especially in mathematics or any other science or discipline, the right names. So let's look at the first flawed example in mathematics, which is the meaning of x in an expression like this. So what does x mean here? Is it a variable? Is it an unknown? What do you think it is? So most of you would say it's either an unknown or a variable. That would be wrong. Some of you would say it's a variable, and that would also be wrong. So what is the correct answer? The correct answer is that x is simply a placeholder for an unknown. And it's not a variable, by the way. So why is it not a variable? X in this expression here is a constant, okay? And a constant is the opposite of a variable. A variable is something that changes. But this x here stands for a value that cannot change. There is only one value that x can be in that expression, okay? Cannot be any other value. The definition of 4 is x plus 2. So in this case here, the only value of x that will satisfy this expression is 2. So x is really a constant and not a variable. And even if there are more values than just one value of x, those values are also constants. They're not variables, okay, because they do not vary. So this expression here is called an equation. It's not a function or anything else. This here is called an equation or an identity, okay? Let's move on. What about functions? This expression here is called a function. Do you think that x or f of x vary at all in this function? Well, what do you think? Let's see. If you thought that either of them vary, you'd be wrong. If you thought that both of them vary, you'd also be wrong. Because for any given x, there is always a given f of x. Okay, so in other words, if you, let's say, chose a particular y or f of x, there's only one x, which is a constant that would satisfy this function. Okay, so x does not vary for that particular y. Okay, and it doesn't. You can't really say it varies for any other x or y, because there is always a pair x and f of x that will satisfy this equation. So if you move this along here, do you see that? None of those x's are changing. They've been there in past perpetuity, and they shall continue to be there indefinitely, whether we're alive or not, or even whether mathematics existed or not, because this function has nothing to do with change, and the values in the ordered pairs are constants. They're not variables. Okay, so it would be very wrong to call x or f of x variables. They are not. They are constants. Now, the mainstream academics, who are actually fools, want you to believe that you can vary these things. Okay, and there's a reason for that. They love to punch holes in functions. So for example, they love to undefine values of x and y in functions like this. And there's a very good reason for that. I'll explain to you in a moment what it is. But if you, for example, have to multiply this side of the function by 1, as you see down here, then at any time you put in a k value there, according to mainstream mathematicians, this will not be defined. See, so for example, let's put a grid in here and let's put this value up here on 1. Now, did you see what happened there? If I take any other k, that's fine. But the minute k is 1, there's a hole in that function. Okay, so but k cannot be 1, and this expression here makes no sense unless it is 1. Okay, so it's really incredibly stupid of mainstream academics to do this kind of thing. But again, I said there's a subtle and deceptive reason why they do it, and it's in order to support their flawed limit theory in calculus. Okay, so in their calculus, which is very bogus and very flawed, what they like to do is keep this x constant and change this distance here, which is h, in other words, vary h. But you see, look what happens. If you have to keep this secant line and the tangent line constant, so if this is 4 and 1.52, any other value except minus 2.48 will render this equation untrue. It will also render this identity untrue. Okay, so if you move this point here of the non-parallel secant line, because this red value here is the gradient or the slope of the red secant line, 4 is the slope of the tangent line. Okay, so if you vary any of those, then they must satisfy this equation. So if, for example, you have a given secant line, let's say this secant line, this red secant line, it has a slope of 1.4. Then you need to have 1.4 in here and 4 here, which means that the difference will be minus 2.6. Okay? There's no other value that will satisfy this geometric identity. So all these here are constants. The secant line is a constant, the tangent line is a constant, and of course the difference between them is constant. Okay? And if you try and say that there's another difference between them besides this one, well, then the historic geometric identity, which I discovered in January of 2020, is no longer true. This says, briefly here, that the slope of a non-parallel secant line, this red line, is equal to the slope of the tangent line plus the difference, okay, plus the difference in slopes. So you could write, in this case here, that for any particular non-parallel secant line, there is a tangent slope and a different slope pair, which will make this equation true. But you cannot keep this guy constant and change these two. Okay, there's no way you can do that, but that's what the fraudulent and hypocritical and ignorant mainstream mathematicians, that's what they think they are, in the mainstream do. And they need it to make their bogus calculus work. But more than that, they especially need holes. They especially need holes because the limit, the epsilonics, that epsilon delta definitions that they use requires that the limit is the same from each side, which means that it's not necessarily defined there. Okay, and so they want to be able to have a hole there. And then, of course, they just add the extra condition that in order for a derivative to be possible at that point, it must also be defined. Do you see? So they're incredibly cranky, incredibly stupid, beyond correction, and it's really something that blows somebody's mind. So that if you multiply by 1, that you can change the value of this expression, because 1 is an identity element. Okay, Now, obviously, if you said k is equal to 0, you can't have times 0 over 0, right? So if you can't have that to begin with, what makes you think that if you started off with, let's say, k9 or any other value of k, that suddenly this value here, x over x, is no longer defined? But it is defined because when we're looking at this expression here, x is 0, okay? But of course we cannot multiply by 0 over 0. So we wouldn't have been able to do that in the first place. Does that make sense? Very well then. This is an important topic, and I wanted to discuss it because a lot of mainstream mathematicians do not understand these things. And of course, in recent days, in the past week or so, you've seen that there have even been a couple of so-called master graduates who don't know what is a factor in mathematics. I mean, it's pretty simple what is a factor, and I've produced a video not so long ago on that. But this terminology has always been wrong, and it's always been used wrong. So much so that you've had idiots like Professor Gilbert Strang of MIT talking about the rate of change of a function. No function has a rate of change. Okay, nothing is changing, not the x's, nor the y's, nor the slopes of the tangent lines. They've been there merrily, forever and ever, long before we even thought of them. Okay, so nothing's changed. They're all there. Very well, I'm going to end this video now. Until next time, my name is John Gabriel. This is a new calculus channel. Goodbye, friends.